Hidden technical debt in machine learning systems. The software engineering industry precedes other industries in its tooling and with the understanding of the importance of dealing with technical debt. For example, software developers use versioning, Markdown for fast documentation, text-to-diagram tools, continuous deployments, and these, among many other tools, are things you don't and sometimes cannot see in other industries. One place where the software industry can improve is the ability to create software in a well-organized form. Instead, today we use processes which try to make sense of coding on the go, like processes such as Scrum. And as Cal Newport said, just imagine a car company, for example, the manufacturing part, where someone runs with the part, or the design part, where someone runs with the part, puts it in the car, in the prototype, then another email comes and they decide to change the color to blue. People are moving around, decisions are taken in mail and in Slack messages all around the day, and they change the parts and the design of the new car all around, and they fix and tweak it. Would you prefer this car or a car that has taken and was generated by a well-organized, holistic processes? So we have ways to improve. We have issues with dealing with Slack messages. We have issues dealing with emails. Sometimes these issues are pretty personal and you should just deal with them. And sometimes it's more on the higher level of being reactive and not paying enough attention. And in general, the software industry just haven't come up yet with the solution to this problem. And you get a deal with the analogy that Cal Newport has given us. However, having said all the above, the software industry takes the lead, the edge, the lead, with the ability to store revisions, with the ability to create diagrams from text with tools like PlantUML or web sequence diagrams, with the ability to have amazing tools for creating documentation, understanding the importance of technical debt, and even coining this term, having active measurements to measure it and to above it. In this place, the software engineering takes a big lead over other industries, even in industries such as electronics. The Hidden Technical Debt in Machine Learning Systems is the title of a great, clear, straight-to-the-point paper published by Google. This paper proposes how quick wins in machine learning, which are taken without proper engineering practices, lead to technical debt, which then leads to slower development and release of features as a result of increased and exponential complexity and unpredictable effects in between the services and the systems. Remember that in ML systems, in many cases, only a small fraction of the code is actually dealing with the learning and the prediction. In many cases, only about 5% of the code is for learning and predicting, while the vast majority of the code in ML systems is just plumbing and more plumbing. This plumbing and glue code is highly susceptible to technical debt. So the paper analyzes multiple common practices, taking today, for example, the separation of the research and the engineering teams which sometimes take place, and many additional practices which we'll review here, and then analyzes the problems that these practices cause in the scope of machine learning. It not only describes the problems, but it also goes ahead to suggest some potential remedies to the technical debt that they uncover. They start by summing up the list of main technical debt. They describe what are the components, what are the technical debts that we usually see, and this is the list. Boundary erosion, pipeline jungle, entanglement, hidden feedback loops, undeclared consumers, data dependencies, configuration issues, changes in the external world, and a variety of system-level anti-pattern. I really wish there were more papers like this one, because most of the papers in ML deal with this algorithm and we found and we have improved these algorithms, but guys, we have technical depth here to handle. So, thank you, Dimitri Ebner. Vinary Chandri, Michael Young, Jean Francis Cuspe, Dan Dennison, you have really created a masterpiece paper here. So, deploying and developing ML systems should have, according to the paper, a similar technical debt reduction mechanism just as any other software engineering have. Remember that we have 95% of the code dealing with clue code and dealing with plumbing. The technical debt metaphor, to remind us, was coined by Ward Cunningham in 1992. This is the long-term cost of taking short-term technical debt just like any other debt. The mitigation to technical debt is in two parts. The first, take existing technical debt and reduce it. The second, invest actively now in order to reduce technical debt in the future. Reducing technical debt is usually paid with refactoring, improving unit tests, deletion of dead code, reducing dependencies, tightening APIs, and improving documentation. Deferring any such payment results in the same way of delaying money debt. The compounding interest is dangerous because the technical debt compounds silently until you can't do any progress anymore. ML systems especially tend to have a lot of glue code. Generic ML packages even more tend to be affected by the external world as input to these models changes the models when they learn. The paper focuses on ML systems technical debt and claims here that we can accumulate even more technical debt in such systems, which is more dangerous than standard systems. Due to the nature of the ML systems, we accumulate more debt. In general, the debt in ML systems tend to accumulate in the system level, which is more difficult to notice because we have a pipeline of data, separate processes, and debt is in between and among them. So the most obvious piece here is that technical debt for ML is mainly occurring on the system level, which is harder than the product level. ML systems tend to have the case property, CACE property, where case is changing anything changes everything. And we get a lot of complexity in this way. ML systems tend to be entangled, meaning we have a mix of signals coming in as input to our model. Sometimes the whole purpose of the model is to take multiple features, multiple disparate features such as x1, x2, x3, and so forth. In addition, you have at the same box or model hyperparameters, settings, sampling methods, thresholds all in the same box, not isolated. So where is your best practice solution? One mitigation to this is to serve ensembles of models where each models handle a specific aspect of the problem. However, this is only useful in cases where the sum problems decompose naturally, and this is not always the case. There are many cases where correcting one problem with system A could cause a problem in system B. For example, let's say you have system A, which you corrected, it's bought too many stocks, and now it affects system B, which takes as an input the number of stocks purchased. ML systems are highly dependent in many cases on incoming data for the regeneration of models and then for prediction. What this means is that any instability in the input signals which cause the instability in the output, sometimes this is good, but sometimes this is additional instability on the system. And as we said, an improvement in system A can cause instability then in system B because their signals are now different. A mitigation that appears in the industry is to assign a version to the data model so that you can change the models as a whole after you have tested it. Just like in software releases, if when you release a software project you have a specific revision that crosses all the projects and all the boundaries and you test on it, then you know it's a good model that you have shipped. And without such tested snapshot as a whole, this can be at least a partial mitigation. In standard software engineering, we can have some modules or code that are dead code path. When we reduce the technical debt, we delete those. And we have the same problem in ML systems, dead code paths. However, in ML systems, they can hide, because these dead code paths could be not dead code paths, they could be features that just don't contribute enough to the output to justify the complexity that they induce. They can also come up as bugs. When the input changes, let's say all stock symbols now have a prefix. This would not be a good day for the models. This is especially true for ML systems, as you tend to do experimental and experimentations sometimes or many times, which end up in dead code or dead features, which you need to clean up. In addition, we have more hidden feedback loops in ML systems because one system affects another. So while in software you can draw the circles and the arrows in between the systems, in ML systems it's more hard because it's like invisible. One model puts a stock on the top, while another one picks up and decides to reduce some other number, affecting back the first model. Another major technical debt is the pipeline jungle. The pipeline jungle is a special case of glue code. This involves all the data preparation. The problem is that as you add additional signals, the pipeline jungle evolves. You have another data source, another join, another step, and then you end up with this untested, unverified pipeline jungle, which is a pile of data coming in and out in steps where it's far from a well-designed, holistic, clean piece of a pipeline. The way to mitigate pipeline jungles is the same as avoiding any other jungle in engineering projects. By taking a holistic approach to the ML system, designing and re-evaluating it, the main point is to re-evaluate it as a whole. Re-evaluate the ML system as a whole to avoid pipeline jungles. When you work with ML code, usually you see data frames, but there has to be standard data modeling and relationship declared between the objects. Otherwise, you have an abstraction depth. The abstraction depth, technical depth, makes it harder both to understand the system and to evolve it. There is a well-known smell for it, named the plain old data type smell, where you see a lot of integers and string data types used instead of proper modeling. Additional smells for general ML technical depth are the multiple language smells, where you start with one computer language with data scientists or for experimentation, but when you get to production, you move to another language that engineering use. This leads to huge amount of time wasted moving in between the languages, practically rewrite. Another technical debt deals with the configuration of ML systems, and we have a lot of them, the hyperparameter settings, which you tune. Once you start having a lot of this configuration, it becomes actually coding with configuration. Configuration becomes your computer language. If you have configurations like this, then you must be able to have proper tooling, like tooling for computer languages, the validations, tests, CI/CD, versioning, code review for configurations, and all this. Another technical debt is the fixed thresholds. The fixed threshold, the technical debt, could be fine for a static system, but usually ML systems in particular are dynamic systems. So this is a decision threshold, which are tweaked manually. But with new data, there is time-consuming effort to re-update and evaluate them. To sum up, ML systems tend to incur technical debt even more than standard systems. This is both because of the lack of education about ML technical debt, but it's also because of the specific nature of ML systems, where it's harder to reproduce the state as it changes with the external world changes. The cultural division between researchers and engineering practices should be fixed. If you don't think you are ready to adopt today the technical debt reduction, at least start by measuring it. How hard is it to change features? How much time do you invest in thresholds? How easy is it to change configuration without surprises? Does improving one model has a downside on another? How quickly do new team members are being effective and understand the systems? If you have issues with this, then you should start dealing with the ML technical debt. So again, thank you for writing such an amazing paper on the hidden technical debt in machine learning systems.